Hello and welcome back to Math 360. Today we are going to be continuing our discussion of species interactions models, and we're going to be thinking specifically about resource competition, which we introduced in the last lecture. Okay, so by the end of today's lecture, you should be able to understand what it means to say we have an equilibrium in one of these models, how we linearize that, and this is involved in linear stability analysis, where we use something called the Jacobian matrix, and also the Routh-Hurwitz criteria that help us to understand the stability of these systems. Okay, so a brief recap. Last time we introduced the Lotka-Volterra competition model, not to be confused with the Lotka-Volterra predator-prey model. And this is a model of species interactions, especially looking at two species that are competing for a shared resource. We talked about, how we can construct this model, and now we're going to be focusing more on how we can analyze it. So essentially the process, if we want to do some analysis on the system to understand what happens in the long term, typically we want to find some equilibria if the model has any. We want to take a similar approach that we did in one dimension. We want to linearize the system close to that equilibrium. So, for example, if we have a nonlinear system, we talked before about how if you zoom in close enough on that nonlinear system, just like zooming in on the surface of the Earth, if you zoom in enough, everything starts to look linear. So essentially, we're looking about the stability close to an equilibrium. We did this in one dimension, now we're just extending this into two dimensions. We're also going to potentially then determine if and how a small perturbation, so a small change in our system close to that equilibrium grows or decays. So we talked before about imagining you are standing on top of a hill or in a valley, and you have a ball, and you push that ball a little bit away from the top of the hill or from the bottom of the valley, and then you want to see if that ball returns to where it started from, which you would in the valley, or if it continues moving away, which you would on the top of the hill. So those are examples of something being stable or unstable. In one dimension, it's relatively straightforward because you can only have these two possible outcomes. Something is stable or unstable in a one-dimensional continuous time system. But things are more complicated when we have two dimensions. We can have things like oscillations that could grow or decay. We could do lots of different things, essentially, when we start moving into two dimensions. We need to account for those now. Okay, so let's go back to our resource competition model. Recall that we had non-dimensionalized it in the last lecture, and so now we have these two equations here where U and V are our scaled population densities for these two competing species, and we have parameters A and B that are both positive, and they give the relative strengths of interspecific competition, so competition between the species. And then we have this other parameter S, which tells us about the relative rate of intrinsic growth for species 2 compared to species 1. And we non-dimensionalize this model because it reduced the number of parameters from 6 down to 3 without us having to fundamentally change anything else about the model. So mathematically, this is equivalent to the full model with 6 parameters. So if we want to analyze this model, how might we go about doing it? Well, we already said we might want to do some algebraic analysis. So that could involve doing things like finding equilibria and carrying out linear stability analysis, which I'll abbreviate that. We could also do some geometric analysis. Now, we did geometric analysis in our simple one-dimensional models as well. In continuous time, we looked at phase line diagrams. As we're in 2 dimensions here, we'd be thinking about phase plane diagrams or phase portraits. The other thing we did in one dimension was we looked at some numerical analysis. So, for example, using Python, MATLAB, programs like this, to understand what's going on by, say, plotting time series or even by solving these systems for particular parameter combinations. So different ways in which we can go about analyzing these models. Today we're going to be focusing on this algebraic analysis, and then we're going to be leading into some geometric analysis at the next lecture. Okay, so the first thing I wanted to talk about today is null clines. And these are used both essentially in our algebraic analysis and in our geometric analysis. So in general, imagine we have a system of two ODEs that are coupled. So you've got dx/dt as some function f of xy, and dy dt is equal to some other function g of xy. Now, a null cline of this system satisfies either f of xy is equal to 0 or g of xy is equal to 0. So what is this interpretation then of a null cline? Well, if we have either f of xy is equal to 0 or g of xy is equal to 0, then that means that one of our ordinary differential equations is equal to 0, but the other one could be changing. So this means that, say, dx dt is equal to 0, but dy dt is not equal to 0. So only one variable is changing along a null cline. This will be very important when we come to look at our geometric analysis using phase planes. So what we can think about really is these x and y variables, they might be describing something like change in the population size. RODs will be describing the change in the population size of two species, say there are competitors. So these are their relative densities x and y. And if we say, assume that we are at some point here, we have some value for x, some value for y. This is some coordinate. It's called x0, y0. Well, at that point in our two-dimensional plane here, we have a value for dx dt and a value for dy dt. And so that's really telling us some rate of change. Again, we're going to come back to this when we talk about our phase planes. You can think of a vector in this plane, which is telling you where you're moving to next. So you're x1, y1. Now, because we're in continuous time, we're not making these actual jumps, but it's telling you the instantaneous rate of change. So how you are moving. Now, what's a null cline doing? Well, a null cline is saying, okay, we're only ever moving up or down or left or right. Why is that? Because if f of xy is equal to 0, then that means there's no change in x, so we can't be moving left or right. So you must only ever be moving up or down whenever f of xy is equal to 0. Likewise, when g of xy is equal to 0, then dy dt is equal to 0. So we can't be moving up or down, we can only be moving left or right. Now, our other variable can be changing, which means that a null cline, say, describes some line or curve in this space where only one of our variables is changing. So suppose we have a line like this, and suppose this corresponds to f of xy being equal to 0. Well, that's saying that on this line, we can only move up or down. So those little arrows that I had, the arrow I had before from x0, y0, going in some direction and going up and some direction going to the right. When we're on a null cline, we can only go, say, up or down or left or right. Okay, so there's no horizontal component in this example here. If instead this was a null cline where g of xy is equal to 0, then there's no change in y. That means that we have to be moving left or right. So we could only be moving in the horizontal direction as we pass through this null cline, or as we move along it. We're only ever moving left or right. So these null clines essentially help us to simplify the problem when it comes to sketching our phase planes. So we'll come back to them, the geometric interpretation, in the next lecture. For now, we're going to be thinking about how we algebraically find our equilibria. And essentially, when we're finding our equilibria, we find our null lines along the way. So that's why we're talking about them at this stage. So why do we do that? Well, if we know that f of x, y is equal to 0 along a null line, or g of x, y is equal to 0, then when our null lines intersect for these two different variables, in other words, when f of x, y is equal to g of x, y, and they're both equal to 0, that means that we have an equilibrium. Okay, so when both of these things are equal to 0, we have an equilibrium. So the idea then, if we want to find equilibria for a particular system, is that we can find the null lines for one species and then substitute those into the ODE for the second species to find when those null lines intersect. Okay, so let's think about our competition model. We want to think about null lines for species 1. So du dt is equal to 0 when u times by 1 minus u minus av is equal to 0. So this is just from the competition model that we had at the beginning. So what does this tell us? Well, that means that either u must equal 0 or 1 minus u minus av is equal to 0, which we can rearrange to have as u is equal to 1 minus av. So these are my two null lines for species 1. And they just describe straight lines in this particular case. There's nothing specific as to why they have to be straight lines. They could be curves, but in this particular example, they would turn out to be straight lines. So u is equal to 0 is just a straight line along the vertical axis where we have u, our species 1, extinct, and our other null line is a straight line where there is a relationship here between u, a, v, and a constant. Okay, so we have our null lines. Now let's think of these two different cases and substitute them into our second equation. So let's think about our first case. If u is equal to 0, so that's our first null line, and we're assuming dv dt is equal to 0, that implies that s times by v, that's by 1 minus bu minus v is equal to 0. This is just my equation for dv dt, set to be equal to 0. If we have u is equal to 0 and this is equal to 0, then that implies that we have s times by v times by 1 minus v is equal to 0. In fact, we can get rid of this s at the front because that's just a positive constant. And therefore, v is equal to 0 or v is equal to 1. So if u is equal to 0, then either v must equal 0 or v must equal 1. So we have two equilibria here already. Now let's think about the second scenario. If u is equal to 1 minus av, this is the other null line from above, and dv dt is equal to 0, then this time we're going to have v times by 1 minus, in fact, we'll have the s still out the front just for completeness here, s times by v times by 1 minus b, u is now 1 minus av, minus v, that's equal to 0. So again, what do we learn from this? We learn that either v must equal 0, or the thing in the brackets must equal 0, which we can expand to be 1 minus b plus abv minus v is equal to 0. We need to do a little bit of algebra now. Let's bring this over here. So we can write 1 minus b minus v, that's by 1 minus ab, so take out a factor of v is equal to 0. If we take this term here over to the right-hand side and then divide by the 1 minus AB, we can have V is equal to 1 minus B over 1 minus AB. This is only true for AB not equal to 1. If AB is equal to 1, then we can't divide by 0. So this is only true for AB not equal to 1. Okay, so we've got a value here for our V, but we also need to think about what is our corresponding value of U. So now we can substitute this back into our equation here. What we're really doing here is we're solving two, in this case, linear equations eventually, because these null lines are straight lines. We end up solving these two equations simultaneously. So we find our value for V. We want to find out what our corresponding value for U is. So we can say, since U is equal to 1 minus AV, U is equal to 1 minus A times by 1 minus B over 1 minus AB, which we can all bring over one bracket. So we're going to have this 1 at the front, going to be a 1 minus AB. We're going to have a minus A, so that's this A times by this 1. And we're going to have a plus AB. For 1 minus AB, these ABs are going to cancel, so we end up with 1 minus A over 1 minus AB. So we now have 4 equilibria in total. So we can summarize them, and it's always good to have a bit of a summary at the end. What are our equilibria in this system? Well, we had UV being equal to 0, 0. So we see that from here. We have the U is equal to 0, V is equal to 0. That's one of our equilibria. We refer to this as a trivial equilibrium because both of the populations are extinct. What else do we have? We have this case here. U is equal to 0 and V is equal to 1. So U is equal to 0, V is equal to 1. This is a semi-trivial equilibrium. It's semi-trivial because one of the species is extinct, so essentially we're no longer in a two-dimensional system. We're back down to a one-dimensional system. What else do we have? We haven't actually fully described all of the equilibria here because we did have this case where this U is equal to 1 minus AV implies that V could be equal to 0. If that's the case, if V is equal to 0, then the minus AV is going to go to 0 as well. So we can have that U is equal to 1 and V is equal to 0. Again, this is a semi-trivial equilibrium because one of the populations is extinct. And then finally, we had U is equal to 1 minus A over 1 minus AB, and V is equal to 1 minus B over 1 minus AB. Again, for AB not equal to 1. And this we refer to as our non-trivial coexistence equilibrium. Coexistence or non-trivial. In fact, we should go a little bit further than rather than just saying for AB not equal to 1. We should be saying when is the coexistence equilibrium biologically realistic. So this AB not equaling to 1 is saying that it's mathematically required. But for it to be biologically realistic, we need to have both our U and our V being positive. So for both of these terms here, the 1 minus A over 1 minus AB and the 1 minus B over 1 minus AB, we need either A and B to both be less than 1, in which case everything on the numerators and everything in the denominators is going to be positive, or we need A and B to both be greater than 1. If that's the case, then the numerators are both negative, but then the denominators are also both negative, and therefore the negatives will cancel each other out, and we'll end up with U and V values that are both positive again. Okay, let's think about stability now. So in our one species models, we linearized around our equilibria, essentially turning our nonlinear problem into a linear problem or approximating, and then seeing if any small perturbations, small movements away from our equilibria would grow or decay. And we did that by looking at the sign of the derivative of our growth rate. Now, essentially, we're going to follow a very similar idea here in our models with two species, but now we need to consider perturbations in both of those species. So rather than a perturbation moving us just along a line, we need to be thinking about perturbation moving us in 2 dimensions. So essentially, we need to look at something called the Jacobian matrix here, which is a way of linearizing our system in 2 dimensions. So we're doing the same thing, but we're having to think about matrices now, whereas because we're in more than 1 dimension. So if we say for a perturbation x of t, this little arrow overhead is indicating it's a vector, is equal to our state vector y minus y star. So this is all in vector notation here, and this corresponds to a system, say dy dt is equal to some function of y with f of y star equal to 0. So this is all in vector notation here, just so we're clear. So we're perturbing in all of our dimensions. We can write down a linear system dx dt is equal to j times by x, and this j is our Jacobian. So this is doing linear stability analysis in more than 1 dimension now. So the stability of this equilibrium is then determined by the eigenvalues of the Jacobian. The reason is given down here, which I'm not going to go to in this lecture here. If you have met this before, this idea that we can describe the general dynamics of a linear system in this form, which I'll highlight here at the bottom. And this is saying if we have eigenvalues λ1 and λ2, then our perturbation will grow exponentially or decay exponentially according to this equation here, if they are real and distinct eigenvalues. It's a little bit more complicated if they are repeated real eigenvalues or if they are complex conjugates. When they are complex conjugates, we end up with trigonometric terms in our general solution, which tells us that we're going to have oscillatory dynamics. We're going to focus on applying this rather than how we derive this particular solution. Okay, so we need to look at our eigenvalues of our Jacobian matrix. Our Jacobian matrix is just going to be some values here, for example, A, B, C, and D. These are just some numbers. And immediately, if we have a 2 by 2 matrix like this, if we have, say, a matrix with a 0 on either of our off-diagonal elements, so here, for example, or if we have a 0 here, or if we have a diagonal matrix where there are zeros in both of those places, then we can immediately read off our eigenvalues as the elements on the main diagonal. So in this example here, our eigenvalues would just be A and D. So that's one way in which we could potentially look at the eigenvalues, and then looking at the sign of these, and that would tell us whether our equilibrium is stable, unstable, or could be a saddle. Talk about that a bit more in a moment. If we're not able to do this, then we could find our eigenvalues by using the characteristic equation, where I is our identity matrix. Regardless of how we find our eigenvalues, we can summarize the stability of our model depending on what those eigenvalues are. Okay, so if both of our eigenvalues are negative, then we have something called a stable node. And that just basically tells us that if we have some equilibrium here, all of our trajectories locally are going to be moving towards it. So this is just like a stable equilibrium in one dimension, at the bottom of a valley, everything moves back towards that point at the bottom of the valley. The contrast to this is an unstable node. When both of our eigenvalues are positive, that means that our perturbation is going to be moving away, so all trajectories will be moving away. And then if one of these eigenvalues is positive and one is negative, then we have something called a saddle. So this is a little bit more complicated, but this is basically saying if we have an equilibrium here, then in one direction, we're going to be pulled towards our equilibrium, but in the other direction, we're going to be pulled away. So we're pulled towards this equilibrium, but then pulled away from it. So this is also an example of an equilibrium that is unstable. It's unstable in a different way to an unstable node. So we're pulled towards it, but then we're pushed in one direction and we're pushed away from it in the other direction. So that's what happens if we have real distinct eigenvalues. We're not going to be talking about cases where our eigenvalues are real and repeated, because that's essentially a knife edge scenario. And typically we're not going to focus on knife edge scenarios in this course. The reason being that knife edge scenarios typically aren't very biologically realistic. So let's think about what happens if our eigenvalues are complex conjugates. So remember that if we have eigenvalues if our eigenvalues of this Jacobian matrix here are complex, and they'll appear as complex conjugates. So for example, we could have lambda I is equal to alpha plus beta I, plus or minus beta I. So these would be our two eigenvalues. They have the same real part, and they have the same imaginary part, but we have plus beta I here and a minus beta I. They're complex conjugates. Okay, so if we have both of the real parts of, the real parts of both of these complex conjugates are negative, then we have a stable spiral or focus. And that's saying if we again have our equilibrium here, then we are going to be spiraling in. It's like water going down a drain. If we have both of the eigenvalues having positive real parts, then we're going to have an unstable spiral or focus. And in that case, we are going to be spiraling out. And if the real part is equal to 0, then we have center. Spell it here in the US way. So a center basically tells us that we have an equilibrium where we have ellipses. I'll draw them purposefully not as circles here, so that we don't get confused in thinking that they have to be circles. Essentially, the amplitude of these oscillations are neither growing nor decaying. And where which of these different orbits you end up on depends on your initial conditions. So this is actually something that's structurally unstable, and we'll talk about why there are problems with this later on in a future lecture when we talk about predator-prey models. So these are all the different types of outcomes that we can get. Essentially, if we have real eigenvalues, then we don't get any oscillations. We don't have, in these cases here, stable or unstable nodes, or a saddle, which is also unstable. Just to make sure it's clear that a saddle is unstable. And if we have complex eigenvalues, then we have some sort of oscillation. So things are either spiraling in, spiraling out, or spiraling, or rather going around in an orbit that never grows nor decays. Okay, so we can find our eigenvalues by looking at our Jacobian matrix. Sometimes we can read them off straight away. Sometimes things are a little bit more complicated, and we can't read them off straight away. For example, if A, B, C, and D here are all positive, we wouldn't be able to read them off straight away. In that case, we could find our eigenvalues by solving the characteristic equation. If we don't actually care exactly what those eigenvalues are, and we just care about the sign of those eigenvalues and something a little bit more about the structure of our Jacobian, we can just look at the trace and the determinant and use those, the sign of those values to tell us something about the stability of our models. So if we have a Jacobian like before, A, B, C, D, we can define our trace, which I'll call here tau, to be equal to A plus D, so the sum of the elements on the main diagonal, and then our determinant, which I'll call delta, is going to be A times by D minus B times by C. Now, the Routh-Hurwitz criteria are really useful because they tell us about our eigenvalues based on the signs of our trace and determinant. So if our trace is negative and our determinant is positive, then we end up with our eigenvalues having negative real parts. And this means that whatever happens, we have something that is stable. And if either our trace is positive or our determinant is negative, then that means that we have something that is unstable. So this top one here, it could be a spiral or a node. Here we could have a spiral or a node or a saddle. In fact, if our determinant is negative, then we always have a saddle. If instead we have our determinant is positive, then we need to do a little bit more digging by looking at the difference between our trace squared and 4 times the determinant. The reason for this is because when we end up solving our characteristic equation, we end up with a quadratic equation because we're in 2 dimensions. And when we use the quadratic formula, we end up with tau squared minus 4 delta under the square root. So this is in our solution for our eigenvalues. And so whether this tau squared minus 4 delta is positive or negative tells us whether we're going to have real or complex eigenvalues. So when tau squared minus 4 delta is positive, so if tau squared is greater than 4 delta, then this term, which is known as the discriminant under the square root, is going to be positive, so we have real eigenvalues. And that means we have a node. So this is just for these 2 cases here. And if tau squared is less than 4 delta, then this term under the square root, the discriminant, is going to be negative, and so we're going to have complex eigenvalues. And so we'll have a spiral or a center. So the nice thing about the Routh-Hurwitz criteria is that we don't have to necessarily worry about finding our eigenvalues. We just need to look at our trace and our determinant and the relationship between them, and that will tell us about the stability of our equilibria. Now, all of this can be summed up in a diagram. If we think about the sign of our trace and our determinant varying, when our determinant is negative, then we always have a saddle. When our trace is positive and our determinant is positive, then we're always going to end up with something that's unstable. Whereas if our determinant is positive and our trace is negative, we always end up with something that is stable. And if we're in one of those scenarios, whether we are above or below this curve here tells us whether we have real or positive eigenvalues. So this is when we are above this curve, our determinant, 4 times our determinant, is greater than our trace squared. And so in this region here, we're going to have things that oscillate because we have complex eigenvalues. Whereas when we're below this curve, our trace squared is going to be greater than 4 times our determinant. So we're going to have things that don't oscillate. So we have either stable or an unstable node. And then finally, this line here, when we are above this red curve, and we have our trace squared being greater than 4 times our determinant, and our determinant is positive by definition here, we are going to have a center. So sometimes people confuse this diagram to assume that they also have a center down here. That is not true, because you will only get oscillations when you're above this red curve. So this center here only refers to the bit that I've highlighted there. So this diagram nicely sums up, if we know our trace and we know our determinant, what are going to be the qualitative dynamics of our system. Okay, let's go back to our resource competition model and do a little bit of analysis. So we can find our Jacobian. So our Jacobian matrix is going to be taking the partial derivative of each of our equations with respect to our state variables, u and v. So in the first case, we're going to have 1 minus 2u minus AV. We're going to have a minus AU here, a minus BSV, and an S, that's 1 minus BU minus 2B. So if you need to recall, we have our equations. Du dt is f of u and v, and dv dt is equal to g of u and v. And our Jacobian is equal to the partial of f with respect to u, partial of f with respect to v, partial of g with respect to u, and partial of g with respect to v. Okay. So if you're not sure how I derive this, have a go at deriving this yourself. That's simply calculating partial derivatives from our competition model that we had at the beginning. And we can note here that we can actually write these terms in a slightly different way. If we note that 1 minus 2u minus AV is equal to 1 minus u minus AV minus u. And likewise, we can write 1 minus BU minus 2B is equal to 1 minus BU minus V minus V. So all I've done is I've taken out one of these U's and V's. And the reason I've done that is because we're going to be looking at our coexistence equilibrium. If we go all the way back up, when we looked at our null-Kleins, if we look at this equation here, first of all, we know that if we're at our coexistence equilibrium, then for du dt to be equal to 0, this term in the brackets must be equal to 0. So 1 minus u minus AV must equal 0. And likewise, if we are at our coexistence equilibrium, we need dv dt to be equal to 0. And so this term here must equal to 0. And this here was a u. So you had 1 minus bu minus v is equal to 0. Why have I done that? Well, if we go all the way back down here, if I rewrite these bottom left and right terms like this, so I'm going to write them out as 1 minus u minus AV minus u minus AU minus BSV and 1 minus BU minus V minus V. We also have an S in this bottom term here. That means that if I look at my coexistence equilibrium, which I'll shorten to U star, V star, and evaluate my Jacobian at this equilibrium, so J evaluated at U star, V star, it means that this term here has to equal 0, and this term here has to equal 0. So at our coexistence equilibrium, I can now write this as minus U star minus AU star minus BSV star and minus SV star. That's just a little trick that we use in this particular case because we know that U and V can't be equal to 0, so these terms here must equal 0 from our original equations. Okay, so we've got our Jacobian here. So I can write down my trace here in terms of my U star and V star without having to do anything else at this particular moment in time. So our trace here is going to be minus U star minus SV star. And by definition, U star and V star are both positive. So we already know this has to be negative. So our trace is negative. That tells me if I go back up to this diagram here, my trace is negative. I can already tell that I am somewhere on this side. I have a stable spiral, a stable node, or a saddle. Okay, what about our determinant? Well, our determinant here is going to equal product of the elements on the main diagonal. So we have minus U times by minus SV, so we're going to have plus SUV. And we're going to have minus the product of the elements on the off diagonal, so we're going to have minus, and then a minus A and a minus B, they're going to cancel out. So we're going to have the signs are going to cancel out here, so we'll have a minus A times by B times by S, again, and a U and a V. So we can take out this common factor of SUV at the front. We have that times by 1 minus AB. Now, if we go, again, just back up a little bit to when we talked about our coexistence equilibrium. For this coexistence equilibrium to be biologically realistic, we need either AB to be less than 1 or AB to be greater than 1. So let's think about how this relates to these two scenarios here. We need to look at the sign of our determinant. What can we say? Well, we know that AB being equal to 1 isn't possible, but we have that delta is going to be less than 0 if AB is greater than 1. Give us a saddle. And this is not just AB being greater than 1, we actually need A and B to both be greater than 1. And that's because we had up here that our coexistence equilibrium is only biologically realistic in these two scenarios here. So either both A and B have to be greater than 1 or A and B have to be less than 1. So if AB itself, the product of A and B, is greater than 1, then both of these have to be greater than 1. So in this case, we have a saddle because we have a negative determinant. So on this graph, this diagram up here, we're in this bottom region here. We have the saddle. Okay, let's think about what happens to get a positive determinant. Well, to get a positive determinant, this 1 minus AB has to be positive, so AB has to be less than 1. In other words, A is less than 1 and B is less than 1, based on our conditions for the coexistence equilibrium to exist. So now if we go back up to our diagram here, we can have a negative trace and a positive determinant, which means we're in this quadrant here. So we either have a stable node or a stable spiral. And to work out whether we're in the spiral case or the node case, we have to look at the sign of our discriminant. Otherwise, we need to work out whether we have real or complex eigenvalues. So let's think about our trace squared minus 4 times by our determinant. So our trace was minus U minus SV. So if we square that, we're going to have a U plus SV squared. We want to subtract 4 times by our determinant. Our determinant was SUV times by 1 minus AB. We can drop this bracket here. Okay, so let's expand this out. If we expand this bracket here, we're going to have a U squared plus 2 USB and S squared V squared. We still have this term on the end, 4 SUV. In fact, I'll take out the AB as well. So I've just expanded both of these brackets here. Okay, so we have two terms that look very similar here. So we can add these together. So now we're just going to have a u squared, a minus 2u sv plus sv squared, s squared v squared, sorry. And we have this plus 4ab su star v star on the end. We can now factorize that thing at the front. So we're going to have a u star minus an sv star all squared plus 4ab su star v star. Because we're squaring this term here, this is going to be positive. All of our parameters a, b, and s are positive. Our u and our v are positive. So this is also going to be positive. So our eigenvalues are real because tau squared minus 4 delta is positive. And we therefore have a stable node. AB being less than 1. In other words, when A is less than 1 and B is less than 1. Again, that comes from our condition for this coexistence equilibrium to be biologically realistic. So we have a stable node. So if we just go back up to our diagram for a second here, what we've shown just now is that we have our trace being negative, we have our determinant being positive, and our trace squared minus 4 delta is greater than 0. So that means we are below this red curve here in this shaded region. So we have a stable node. So next time we are going to be looking at some interpretation of this model and geometric analysis.